In this next section we're going to talk about electric potential energy. We're still talking about electrostatics, talking about a charge can exert a force on another charge, and electric field as a way to describe how a charge affects the region of space around it and can in turn exert a force on another charge. Now with energy, we're kind of building like we did in the first semester physics class, when we talked about forces, and those forces cause an acceleration according to Newton's second law. And then after the section on forces, we talked about energy and work. So we're building on that similarly this semester. So we talked somewhat about forces as far as charges are concerned, and now we're going to talk about energy. Now, energy, we started actually fundamentally talking about the concept of work. Now, you might recall work is force times distance, but keep in mind it wasn't quite that simple. Work is the force dotted with displacement. So the dot product tells us that it is only the force that is parallel to the displacement. So it multiplies the component of the force that is parallel to the displacement, because that is the only component that was responsible for either putting energy into the system or taking energy out. So as a reminder, work is a transfer of energy either in or out of the system. And our system could be a single object. Like I push a box, so my system was the box. But the only way I could apply a force that would give the box energy is if I pushed parallel to the displacement, or at least had a component that was parallel to the displacement. So, sorry, let me finish this bottom statement. So the dot product multiplies the component of the force that is parallel to the displacement. Work was only done if the force did cause a displacement, so the object physically moved from one place to another. The dot product is also a scalar. It's not a vector. So positive work was when energy went into the system. Negative work, energy came out of the system. Negative work, we saw that fairly often with friction, like kinetic friction. It took energy away from the system, and it did turn it into another form, the thermal energy. But it was removed in terms of the kinetic energy. So we had the work kinetic energy theorem, where we said the net work on the object or system was equal to the change in kinetic energy of the system, where the kinetic energy is 1/2 mv squared. So the change in kinetic energy would be the final kinetic energy minus the initial. So what we're going to look at now is we're going to look at how we can apply this in terms of charges and electricity. So again, this work, the force had to act parallel to the displacement. We did have to integrate if the force varied with position. And that's why the fundamental equation for work has the integral in it. So we have to integrate if the force varies with position. Okay, so we're going to look at two situations. We're going to look at situations where the force is constant. If the force on our charge is constant or uniform, we can pull the force out of the integral sign. Integral of dot ds is going to be some sort of delta s, a displacement. So this is still a dot product, meaning we have to multiply the component of the force that's parallel to the displacement, and we get a scalar answer. We will also look at situations where the force is not constant. It's varying based on where the charge is. In that case, we do have to integrate, which we will do. But I want to start first with a constant or uniform force. So I'm going to drag this up here. If you think about what we've covered in terms of the previous section, the force on a charge, so I'm talking specifically the electric force on a point charge, can be written as the charge times the electric field that the charge is physically located in. If the electric field is constant or uniform, then the force on the charge is going to be constant or uniform. Well, one good example of a uniform electric field was between two parallel plates. So like a capacitor. It doesn't have to specifically be a capacitor. These plates could have different surface charge densities. A capacitor, though, was defined as two plates with having the same magnitude of surface charge densities. So these plates, one being positively charged, the other being negatively charged, we end up with an electric field in here that is uniform. And I didn't do a very good job of drawing them equally spaced. So between the plates of a capacitor, the electric field is constant. It has a magnitude of the surface charge density of either plate. They have to be the same to be a capacitor. And then divided by our constant epsilon naught. So if we think about having a charge, like a little proton in here, the work done by the electric force as the charge moves in this region where we have an electric field, we could say it's the electric force, which I'll put in Q times E in just a second, dotted with delta S. So Q, E, dotted with delta S. Now again, the dot product means the electric force and displacement must be parallel for work to be done. The proton in this electric field is going to experience a force specifically that is in the same direction as the electric field. That means the electric force does no work if the charge moves, say, perpendicular to the electric field. No work done. The charge moves somehow, like if we could somehow physically move this proton, no work would be done by the electric force if the charge moves perpendicular. Perpendicular to the electric field. And that's the nature of the dot product. The dot product is only accounting for the vectors that are parallel to each other. What this tells me is the electric force will do work as long as this charge is moving in some direction, either with the field or opposite the field. With the way I've drawn it, it doesn't have much room to move to the left, but it certainly could move to the right. That delta S to the right, that distance traveled, then we could say QE delta S would be the work done as long as delta S is the direction that's, the distance to the left or right, specifically lined up with the electric field. All right. Now, I don't know if you recall, but also in Physics 1, we talked about, say, like gravity. The force of gravity, we said, was conservative, meaning the work done by gravity was the force of gravity dotted with the displacement, but ultimately we simply needed to know how much vertical distance, just a delta y, that was covered, because the force of gravity points straight downwards. So force of gravity points straight downwards. An object has to move up or down in order for the force of gravity to do work. And the work done by gravity depended only on where vertically the object started and ended. So, for example, if we were talking about like an elevator car that was moving, say downwards, we would only care about this y direction, how far it moved vertically, and we could say that the work done by gravity would be the force, mg, and then it would be this y distance. This work would be positive if the elevator moved downwards, because the force and the displacement were in the same direction. We can write any dot product equation as the magnitude of these two vectors times the cosine of the angle between them. Meaning, if I drew my displacement starting at the same location that the force of gravity did, the angle between these was 0 degrees. Cosine of 0 is just 1. And so gravity did positive work as an object moves downwards. Gravity's working to speed it up. Now, granted, this elevator car would also have some sort of tension, which would be doing negative work, not allowing the elevator car to just keep speeding up to the ground. Ultimately, though, how much work was done by the force of gravity simply depended upon the force of gravity, mg, and then how far vertically the object moved. The work's positive if the object moved downwards. The work was negative if the object moved upwards. It did not depend on the path taken, meaning it doesn't matter if the elevator car went down and then back up, the net work would be 0 as far as gravity is concerned. Okay, that's what makes force of gravity a conservative force. When we have a conservative force, well, I'll write it up here. If we have a conservative force, we can say the work done by that force can be talked about in terms of what we call potential energy. since the work kinetic energy theorem tells us that work is, the net work is equal to the change in kinetic energy, then the net work can be written as the negative change in potential energy. If you recall, potential energy for gravity, gravitational potential energy, we said mgy. But in order to get a positive work in the example of like the elevator car moving downwards, but y final would be lower, technically we get a lower potential energy. And that's why we see a decrease in potential energy or stored energy, this energy of interaction, in terms of writing out net work. If the kinetic energy is going to increase, potential energy would decrease. We can talk about this also in terms of conservation of energy. If all we have is a conservative force, then there's no change in the mechanical energy of the system. We wrote this also as a U initial plus K initial equals U final plus K final. That's another way to write it. That's perfectly valid. It turns out that electric forces are also conservative, meaning we can say the work done by our electric force can equal a negative change in potential energy. So as opposed to talking about the work done, we could talk about how the potential energy is changing and then relate that to a change in kinetic energy if we wanted to. Okay, bunch thrown at us here at first. Let's come back to this example with our capacitor that we have here on the left. What we're saying here is the work done on a charge, a positive charge, as it moves through this electric field is equal to how much charge we have, how strong the electric field is, and then how far our charge moves parallel, specifically, parallel to the electric field. Now, the work done on a positive charge moving to the right in my picture, the work done is positive. Energy would be given to this proton, this positive charge. Work being positive means energy in. Energy is given to this positive charge. Okay, that means this charge would speed up, which hopefully makes sense. It's headed towards a negative plate. It's attracted to the negative plate. That force is going to cause it to speed up towards that negative plate. It is possible that we could have a negative charge in here, an electron. The electron, of course, doesn't naturally want to move to the right because it's repelled by the negative plate. It wants to move to the left. Its electric force is to the left. So the work done on a negative charge is positive when it moves opposite the electric field. The negative charge will speed up if it's moving towards a positive plate because it's attracted to a positive plate. okay? And it is as easy as just fundamentally thinking about the attraction and repulsion of the charges. If the charge is moving in the direction where it's attracted, then it will speed up. If it's moving in a direction where it is repelled, it will slow down. Okay, so we can, in the case of this capacitor, since the work is going to be QE delta S, and we can set this equal to the negative change in potential energy, we can say that the potential energy, electric specifically, this is specific to a point charge in a capacitor. In a capacitor's electric field. We can simplify this down and just say Q, the amount of charge we have, times the strength of the electric field, times where it is, S being 0, where the electric potential energy would be 0. So let's think about that plate for the capacitor again for just a second. If I have a proton in here, we're going to essentially say the lowest point, even though it's not downhill per se, lowest point, the last place it can get to, we're defining as a potential energy of 0. So we are essentially saying that this location is S equals 0 in that situation. Now, just as a reminder, an analogy, let's think gravity for a second and gravitational potential energy. Gravitational potential energy, as long as we were on or near the Earth, we could say the gravitational potential energy could be calculated as an mgy. And we were allowed to say y equals 0 wherever we wanted. And if y was 0, then the potential energy was 0. So typically, we chose the lowest point, the ground, whatever the lowest point in the problem was, to be our y equals 0 location. We know an object, say this high above the ground, would have a different amount of energy than something higher off the ground. So even if these two objects had the same mass, they would not have the same energy, simply because they were at different vertical heights above the ground. Now, gravity, we can represent gravity by what we call a gravitational field. So similar to charges, we talked about an electric field to describe the force of a point charge would experience if it happened to be in that region of space. So we described the electric field or used it to describe some sort of alteration of space. We can do that with gravity as well. We can draw what we would call a gravitational field that's uniform as long as we're near the Earth, and that would describe how the Earth is influencing the region of space around it. And when we go and put different masses at different heights, they have different amounts of energy specifically because of where they are in this electric field. So this height, I'll call it y1, being smaller than the height y2, this mass would have less potential energy, gravitational, simply because it has a smaller distance to travel to get to the ground. This one would have more potential energy because it is higher. It has a larger distance it can travel before getting to the ground. And we know, hopefully, if we were to release these masses from rest, their potential energy would turn into kinetic energy by the time they reach the ground. And so, conservation of energy. So the height in here is where in the gravitational field. It's the where in the field portion that we're talking about. Okay, let's come back to our capacitor here for a second. I'm going to draw my capacitor differently. I'm going to draw my capacitor so that my plates are horizontal with the positive plate on top and the negative plate on bottom. The electric field between these two plates will point from positive to negative, and it will be uniform. And this is the electric field in here. Okay. Ultimately, what I was saying about S equals 0 and the lowest point, just defining that as no potential energy, if I'm defining this location as 0 potential energy, yet I have a positive charge in here, I know this positive charge is attracted to the negative plate. It is experiencing an electric force that points downwards, and that force would cause the charge to accelerate downwards, speeding up until it got to that negative plate. We're essentially saying this charge is at, it's not really a height, but at a specific location in the electric field that gives it a specific amount of potential energy. The electric potential energy it has right there is based on how far away it is, that positive charge is, from this negative plate. If I took a positive charge and put it, say, down here, so it was closer to the plate, it would have potential energy as well, but the potential energy here would be less than the potential energy it had if it was farther away up here. So where the charge is located in the electric field is a contributing factor to how much potential energy the charge has. And that's what this equation up here is representing, is the potential energy depends upon the charge itself. It depends upon the strength of this electric field and how far away the charge is from that negative plate. Okay, this equation though also works for negative charges. Let me just draw this picture again really quick. So capacitor, electric field, we're still saying, we still can say S equals 0 down here. But let's say I put a negative charge in here. If I place that negative charge anywhere along this dotted line, it's going to have the same amount of potential energy. But since the charge itself is negative, negative charge, the potential energy will be negative. Which is a little kind of weird to think about. When we talked about gravitational potential energy, our energy typically wasn't negative because we defined y equals 0 at the lowest point. And that's an arbitrary decision, by the way. We didn't have to define it there. It doesn't really need to be the lowest point. It just made the mathematical setup easier. So here, our potential energy is negative, but if we think about a charge, negative charge closer to the positive plate, which means farther from the negative plate, this would be another QES. I'll put S2 and S1. This will be a more negative value. Now, since energy is a scalar and not a vector, energy is a scalar. If I'm comparing just two numbers, say a -2 to a -4, -4 is a smaller number than -2. So that means this is less potential energy than this one. This has more potential energy compared to this second point. So potential energy is negative when we're dealing with negative point charges. But a negative charge will naturally want to move to a location where the potential energy is smaller than what it was before. So if the charge is allowed to move on its own, then it will move to a location where the potential energy decreases. And that is completely explained by, well, it's a natural state, but it also, we can see that energy turns into kinetic energy as that happens. So potential energy plus kinetic energy initially would be potential energy plus kinetic energy finally. And naturally, objects want to move or will move from a location where the potential energy is higher to a location where a potential energy is lower. Now, that doesn't mean we cannot launch a charge. So, for example, we could have an electron in here that we gave an initial velocity to. So we make it move to higher potential energy as it goes this way towards the negative plate. So it can move to a location where potential energy is higher, but it will slow down, eventually turn around and go back. So if you want to have this analogy to gravitational potential energy, we know objects will naturally roll downhill when we're talking gravity specifically. With electric charges, you can think of downhill, meaning the direction the charges will want to go is with the electric field if Q is positive. Opposite the electric field if Q is negative. I find it helpful to just think in terms of, we know electric field points from a positive charge to a negative charge. So just to think of it in terms of attraction and repulsion is helpful too for me. And then I'm not trying to memorize if it has to be with or opposite the field. Just think of whether it's attracted or repelled in the direction it's going. Okay, so we're going to be looking at conservation of energy, Keep in mind this equation for potential energy is specific to a constant electric field and defining S equals 0 as the last place the charge would get to. So specifically with this capacitor, we defined S equals 0 at the negative plate as far as this equation is concerned. We can talk about the work. This is just an equation from above. Work as the electric force dotted with the displacement. Dot product we can write as the force dotted with displacement times the cosine of the angle between them. That means a charge, say I come back to this capacitor on the left. If I took this positive charge and moved it over to here, that would be no change in potential energy. No work done by the electric force. So it's only motion with the field or parallel to the field that will result in work done by the electric force, which we can relate to potential energy. So in the next video, I'm going to talk about these locations in the field. We have a specific term we use for that with electricity, and we will talk about that next.